Welcome back to Advanced Algorithms. Last time we talked about fixed parameter tractable algorithms, and after a lot of definitions what that exactly is, we tried to show, or at least give hints why certain problems seem to be hard with that respect. So it seems that we can't find a fixed parameter tractable algorithm. And we've looked at the class para-NP. But we found that, unfortunately, that class is too mighty in a sense, so that too many problems fall into the class, so that too few problems are complete for the class, right? So the class is too powerful or contains too many problems. Therefore, essentially only those problems were para-NP complete or para-NP hard, where even for a fixed value of the parameter, the problem is NP hard already. And our goal with fixed parameter tractability was to subdivide the NP complete problems into those that might at least be easy to solve for small values of this parameter k. So today we'll dive a bit into the parameterized complexity theory, and we'll find that it's a bit involved. We will not do all things in detail, but I want to give you a glimpse of it at least and do a few simple proofs. And just keep in mind that a lot is just not as easy as in the P versus NP case. But at a certain point we will stop and confine ourselves with a certain notion of hardness that's widely believed to imply that a problem is not in the class fpt. And we will not be able to show for most problems that they are complete with respect to the class. We will only show that they are hard with respect to the class. But in terms of is there a good algorithm or not, it will not make a difference. Okay, if the class is too large, that means we should weaken the definition of the class. So you might recall para-NP was the class of all problems that can be solved by a non-deterministic algorithm whose runtime is bounded by the usual FPT thing. So a certain computable function of the parameter, which we don't know anything about, and a polynomial of the input size. Now this f could be humongous, but it must be completely separate, and the rest should only be polynomial. That was FPT. And for para-NP, which simply allowed all steps to be non-deterministic. And it's, yeah, as we've seen, this is allowing too many problems to be in that class. So we restrict it further. We'll actually consider two restrictions. And there are infinitely many more that we will not discuss in detail. Well, first, we've started with Turing machines, and in the very first lecture I talked about computational models. And it turns out that here it's no longer that all the models are equivalent. You have to decide for the right one, and it makes a difference which one you take. For para-NP it was not so important, but here it will become important. I can say up front that you can either take a Turing machine that has multiple tapes, or you can take the non-deterministic RAM that I'll discuss in a second. So the multi-tape Turing machine is, I found it not so intuitive, and it's also, in a second sense, not so nice. So this is maybe the more intuitive part, even though it's maybe technically not as pure and minimalist as the Turing machine. So you remember from the first lecture what a word RAM is. That's essentially, so this stands for random access machine, which means we have an unbounded array of memory that we can access using an index. And each of the memory cells contains an integer, or say a natural number usually. And it's a number between 0 and 2 to the w minus 1. It has a number that has w bits. And for this model to make a nice model in terms of the costs, we want to assume that the word size grows with the input size. That was the model that we discussed about in the beginning. This will not play a big role here, but with that choice, we're essentially in the realm of the uniform cost model. We can essentially add up numbers of this size in a single step with unit cost. But as you'll see below here, we will restrict the size of the numbers so that they're not too large, so that it's not the uniform model in a pure sense, but we restrict it to the sensible range where we don't have humongous numbers without paying for it. Okay, so that was a repetition of what a RAM is. Now we add nondeterminism to this machine. And unlike for Turing machines, where it was a very natural part of the definition, instead of a transition function, you take a transition relation. For these RAMs, it's not as natural, maybe, because they usually have go-to statements that jump to a certain instruction in the program. So you have a program counter that contains the line of the instruction that you're executing, and you can change this counter. So how would you add nondeterminism to that? One relatively simple and clean idea is you add another instruction called guess that for a certain register that contains a certain number replaces this number by a nondeterministic guess that can be a number between 0 and the current content of that register. And the rest is defined as for Turing machines. So we should define what the language is that a certain machine accepts. Then we should talk about how a RAM that only can compute with numbers can compute with strings. But you might imagine that we can easily encode an alphabet as numbers, and then the machine gets the input in the memory in the first cells in the beginning. And then acceptance is defined as before. If there is one non-deterministic computation, one possible computation that accepts, then the whole machine accepts this word. And if not, if all runs are non-accepting, then it doesn't accept. So this is all relatively intuitive. That's why I didn't write it down in too much detail. Now, what is an NRAM that is kappa restricted? So we're talking about a parameterized problem, and we have a machine that, a non-deterministic RAM that decides this problem. And now it is called kappa restricted if it has the following properties, namely it's an FPT algorithm. That's maybe the most natural part. We also restrict the number of non-deterministic steps. These may only depend on the parameter. And that's the main difference to the class before. There we said you can have this runtime, and just a non-deterministic machine with that runtime can be non-deterministic in every of these steps. Now we allow only a function of the parameter here. And then to make it technically sound, well, accessing not more than those registers is basically implied by only having so many steps. But we also require that we don't cheat with the uniform cost model. We never use numbers that are larger than this as well. Okay, as before, these are just some computable functions that we don't assume anything else about. Now we define the class WP. That's simply the class of all problems that are solved by such a machine decided by a kappa-restricted, non-deterministic random access machine. That's our class WP. Now, first, we can use the same kind of reductions that we used before, namely these FPT reductions. to define hardness and completeness for this new class. One should prove that the class is closed under FPT reductions, but that's relatively easy because they essentially are of this kind, only that they don't use nondeterminism at all, if you recall that. So we can define that. But for the class to be helpful in our task to assess the complexity of problems, we should also have a first WP complete problem. Well, last time we've talked about the Drosophila of complexity theory, namely satisfiability. So the first thing you try is, can we find a version of SAT that plays the role of this? Well, an easy observation is that p-SAT, as we've called it before, cannot be one of these problems. Would anyone like to guess why? So we're looking for a complete problem, so a hard problem. Was p-SAT a hard problem if the parameter is the number of variables? It was an FPT problem. Just by the brute force method, you could try all assignments. That gives you 2 to the k, but there's no n in this part. And then for every assignment, you only insert and evaluate the formula, which is polynomial for sure. So you have an FPT algorithm for it, which implies that the problem is in FPT. So it's definitely not complete for this class, because that would require that all these problems reduce to it. And, well, I didn't explicitly say that. It should be obvious that the class WP must be a superset of the class FPT, because on top of, well, we simply add this feature of nondeterminism, right? We can do everything that FPT can, and we can do more potentially. But it might not be surprising for you that it's an open problem, whether it's strictly more. Okay, now if you look at the definition, the number of nondeterministic steps essentially allows you to guess k numbers, or a function of k, but let's remain simple. We allow k guesses. And each of these guesses can be a number, and this number must be something related to the input. So if you think of SAT, what you can do with let's write down the question first. Gives you a few seconds to think about it. Say between 1 and n, whatever. Well, this can identify a subset of variables, but not any subset, but only those of size k. I can choose a subset of size k from n numbers by guessing the indices of k items, right? But I cannot guess all the 2 to the k different versions. Now, this is just to motivate the following definition, but so recall what the weight of an assignment, of a variable assignment was. I mentioned it at the very beginning as one of the examples for parameters. If you have an assignment from the variables given by their index to 0, 1, then this is the number of ones that you assign. was one of the parameters that you maybe found strange at first sight, and now it will reoccur in this lecture a few times. Because we will now look at the weighted satisfiability problem. It's not very intuitive. I hope that this idea that you can, in exactly this way that we defined WP, you can exactly guess k such numbers, might motivate why this is related, but still the problem is a bit unintuitive. We're given a Boolean formula and a number, which is also taken as the parameter, and we ask if there is a satisfying assignment that has exactly this weight k. So we're not interested in whether the formula is satisfiable or not. We're only interested in those specific assignments. Now this is a bit imprecise because it matters a lot how the formula is given. So if I say formula, it's okay, you wouldn't probably think of circuits, but we will need that in a second. And a circuit can implicitly give a formula. So the phi could be given as either a formula as you know it, so a Boolean formula, but these can have different shapes. We've already encountered the normal forms. So any1 or conjunctive normal form or D-conjunctive normal form, where we require each clause to have a specific number, or at least not more than D literals. I know you can cook up many more. You can also give a Boolean formula implicitly as a Boolean circuit. Intuitively, this is just a graph of these Boolean nodes that connected by wires compute a Boolean function. So let me give you an example. We can have AND nodes. We can have NOT nodes. Or maybe I should make them all the same. Now you can connect these. Say an OR node. And then here you can have an output. I will always draw it from left to right. What's the difference between circuits and formulas in terms of complexity? So depending whether or not you directly allow this, if you define Boolean formulas so that equivalence between two subformulas is just a syntactic abbreviation, which you often find, then this is equivalent to saying A and B, or not A and not B, which is fine in terms of existence. But if you have a formula that's given with many of these clauses and you always double the size, note that you have to copy these formulas here, then the size can grow exponentially. So in general, you might know that it's not possible for a certain formula to find if you allow these operators to find an equivalent one in the normal forms in polynomial time, not in the strict sense that the formulas are exactly the same. If you remember the reduction from SAT to 3SAT, then you can find a formula that's equivalent in terms of the satisfiable yes or no sense. But that's a different one that adds new variables. But in Boolean circuits, you can easily do something like this. If you have the subformulas given as circuit, some inputs that compute some output, then you can just connect these twice. And then you might notice that I've exactly built a circuit for this formula. But instead of copying A and B, we have those only once and just a constant number of additional nodes. So that's why, in general, circuits are much more powerful, more expressive, and at least more, in particular, they are more concise. They need less space to express the same Boolean function. So it might make a big difference how you represent the formula. And here's a theorem that says this weighted satisfiability problem for Boolean circuits is WP complete if you parameterize by the weight of the assignment. So it's the problem that we've been talking about before. You're given this formula here implicitly as the circuit and the number k. Proving this theorem in all details involves a lot of techniques from circuit design. So a lot of technical lemmas, how you can construct certain circuits with certain properties. And to make it worse, you also need several simulation results from theoretical computer science that I would not want to go into detail. But I just very, very roughly sketch the proof idea, okay? So this is not something I'll expect you to know in an exam. First, we've defined the class by our non-deterministic RAM machines, RAMs. So you can simulate these using a multi-tape Turing machine. And this already involves making sure that you don't have too large a machine. And then you simulate the multi-tape Turing machine by a Boolean circuit. Which is polynomial in the size of this thing. This simulation is easy also for formulas. That's the way how we proved Cook's theorem. But now we have this multi-tape Turing machine. Yeah, it depends on what exactly you take as input. So, but there's such a simulation. And then, as I mentioned, we need some tricks on circuits. To convert the circuit that this simulation spits out into one that fits our weighted satisfiability problem. So the circuit that comes out here has the property that it's satisfiable as a formula if and only if this machine accepts. But this is not what we need. We need a different way of acceptance, a different way of satisfiability. So let's say this is a circuit C that's spit out by this. And we convert it to another circuit D, so that if the one is satisfiable in the usual sense, exactly when this D is K satisfiable. By which I mean satisfiable by a weight K assignment. So this second step is not extremely complicated, but it would take too much time to go into all the details. But there's a nice simple trick that I might just explain on a conceptual level. You can interpret blocks of these where you pick exactly one variable as So the idea is you take a block of these, and then the variable that's true in that block tells you what number it is. So one of these from the block that represents a number, and then you can convert this to the binary representation of the number and take that binary representation as input to this circuit. So to simulate all different assignments for the original circuit, you transform the binary representation to a different representation of the number, where you just write down all possibilities of the numbers as individual variables and enforce that only one of those is true. Can you imagine how this is meant? So it's not clear how to construct such a circuit, but I mean, I could just promise you it can be done.
We don't get problems with the transformation being in like some kind of, I mean, it's 2 to the power of inputs inside this, I mean.
You don't get these problems because of, well, one thing is that we have Boolean circuits that avoid this copying. And the other thing is you use blocks. So you don't say the whole thing is one large number, but you have certain blocks of certain size. And if you keep the block size small enough, then it's not an explosion. Yeah, I'm skipping many details. It's not well suited for this course. Also because I think we should not spend too much time on this structural complexity theory part, because the main focus should be on algorithms. And we'll come to that not so far from here. But we're still one class away from the good one that we want to define hardness against. The problem is that this circuit satisfiability is again too strong. You can encode a lot in terms of circuit satisfiability, which again means that for many problems that we are interested in, for example, the p-Clique problem parameterized by the optimization, the threshold value, we won't easily find a proof that it's WP hard. And well, for many more problems, we won't find such a proof unless someone shows a great result. So we should weaken the class even further. So already we've just reduced the nondeterminism to only depend on the number of nondeterministic steps only depend on the parameter. And we can do a slight change in the rule by enforcing that for such a nondeterministic RAM, all nondeterministic steps occur at the end of the computation. That seems like a crazy requirement that shouldn't change too much, but it changes a lot, even though it's maybe not very intuitive why it does. So the total number of different computations certainly doesn't change. But it gives you a different factor maybe in the running time. It's not very intuitive. I don't find it very intuitive. But here's the definition. Tail-nondeterministic is just only the last h of kappa steps are nondeterministic. And well, if you go back to the definition of these kappa restricted NRAMs, they're already restricted by some g. Now you can essentially drop the g because we have the h that takes its role. So we only allow the last h of k steps to be non-deterministic. And now W1 is the class of all the problems that can solve by such a machine that only uses these tail non-deterministic computations. We can again define hardness and completeness like we usually do, and we keep the same kinds of reductions. And as before, the closeness, that the class is closed under these reductions, is almost trivial because we only added a bit to the defining machine model. So the reductions may not use nondeterminism. We may use a bit and only at the end, but still we can do anything that the reductions can do. Now we can ask the same question as before. Yet another definition, so a little digression. I always had this idea in mind. Whenever someone defines something new, he should pay a fee for definitions, so that he's compiling some amount of debt that he has to pay back by motivating why that definition makes sense. For these definitions, it's not. I didn't find very convincing motivations, except for the case that they work, showing the hardness of certain interesting problems. So this definition in particular is not very intuitive. I said it twice already. So I owe you a few more motivations and explanations regarding these definitions, and I promise a bit will come. So the question again for this class is, what is the first hard problem or complete problem? Okay, now you may guess what we'll look at first. Which problem might we try to look at first to check if we find a suitable version that's complete? Yeah. Satisfiability. Well, in this case, it's easier to start with another one. Gotcha. But we'll come back to satisfiability in a second. Let's look at this problem. That's because we defined the problem in terms of these non-deterministic RAMs, it might make sense to try to go back to Turing machines and the ordinary versions. So let's consider the following parameterized problem. We have the description of such a non-deterministic, but otherwise ordinary Turing machine given, and also an input and a number, which is the parameter. And we ask whether this machine accepts the given input in at most k steps, which sounds like a very simple problem because k steps, if you bound that, it should be easy. You just simulate the machine. But since the machine itself is part of your input, certain things cannot be assumed to be fixed. Namely, the state space of the machine can be as large as n, if that's the input size. And the same is true for the alphabet it works on. So that means there's not only a constant number of different steps it can take in each time step, but we can have up to n different non-deterministic choices. And if we want to simulate k of these, maybe one more to check if none is accepting or so, then we have a running time like n to the k. And we've decided last time that we should draw the boundary between good and bad algorithms between n to the k and 2 to the k. Right? N to the k was already too much. So the trivial algorithm for this problem is not an FPT algorithm. And in fact, none is known, and we suspect that there's also none to be found. A technicality, if you like, you can omit this input, and in terms, so you can omit the input and say we hardwire this input into the Turing machine, because the Turing machine itself is part of the input, and we are only asking for the machine's output on a single input. We can also just modify the machine at will. So if you like, you can drop this. You can imagine that there's a certain sequence of states and different states that just tell you what the input was like. Well, writing down details might be more challenging or at least messy, but I think the idea is it's clear that something like this can be done. So I would like to give a proof sketch again, maybe a bit more detailed than last time. But this is essentially asking for a translation between the NRAMs and Turing machines. So that's why I think this proof might be a bit insightful or helpful for understanding the differences. So first, we're claiming that this is W1 complete. So the first part is showing that it is in W1. And that means given this Turing machine and the input x and the parameter k, we're looking for an NRAM. Now, how should this machine work? We know that all the usual computational models can simulate each other with polynomial overhead. And we can just simulate m for k steps. And then output whatever the result is. Now, since we only simulate k steps, so the polynomial overhead should be before we first construct all the auxiliary structures that we need for the simulation. And then in the last steps, so to say, we execute the non-deterministic choices of the machine. So that the last part should only add a constant overhead per step that we have to simulate. Otherwise, we are not tail-nondeterministic. This is still the easy direction because we just have these few steps to do. Now for the other direction, the case that this halting problem is hard, we have to show that any other W1 problem reduces to this one. So by definition of W1, we can assume that there's such an NRAM given that decides the problem. So and it's a tail non-deterministic and kappa restricted one, right? So that decides L. Yeah, we can write the parameterized version. Now, for we now construct a machine and an input and a k, so that these are equivalent. This A, the problem with the A is that it can have a potentially very long computation, And then at the end, it does some non-deterministic steps. But for the Turing machine, we have to find a bound on the number of steps that only depends on the parameter k, right? But for the deterministic part, we can pre-compute that in the FPT reduction. So generate, as part of the reduction, the result of the deterministic part of the computation. So I should maybe add the FPT reduction is considering a certain problem. For that, we have this NRAM A, but also a certain instance X. Right? So given A and X, that's why this is possible. Okay, this is not so a good idea to have the same. So this input X is the X for the Turing machine that we have as part of the halting problem, whereas this X tilde is the input of the W1 problem that we are now reducing, that we're transforming to a Turing machine. So we generate X on X tilde. We have this computation. And we can, as part of the reduction, pre-compute what A would have done on this X tilde. And for example, well, what's the state of a RAM? It's the content of all the registers and the program counter. That's all there is to such a machine. And the program itself is given in A in some sense also. So we can essentially write down the state of A before the first non-deterministic step. On the tape of the Turing machine, so, well, we give it as input. So, the Turing machine assumes the input is written on the tape. So, well, okay, we can give a description of that state. The details are again a bit fiddly. And then we generate a non-deterministic Turing machine M that somehow has to digest this description of the state and then executes the last, that simulates this last h of k, h of kappa of x tilde, steps of the non-deterministic RAM. But here, the Turing machine can use its own non-determinism, so this is not a big problem. And well, it's not so clear on the abstract level how we should choose the k, the inputs for the number of steps. But the Turing machine will have some overhead in this simulation, and then we will have to insert h into that. That gives us some function. So k is a certain function f of h of this parameter that we're given. So it's not so clear how to specify this precisely, but there is some function that makes this work. So this hardness proof was certainly a special one, and it's, to some extent, it plays the role of Cook's theorem, where you also have, for one time, have to go by foot and show for all problems there's this reduction. We will usually not use it like this. The problem is that we're still on such a computational model level. So if you would now try to show that, say, the p-Clique problem, so is W1 complete, you would have to simulate a Turing machine into the Clique problem. I think I've seen even an explicit proof that goes this route, but it sounds like a bit more effortful than what we do. If you take a look at the classic world there, the 3-SAT problem has this nice property that it usually is easy to simulate in all kinds of combinatorial problems. So we would like to have, again, something like SAT. So this is only the first step. Now here's the theorem that we've just proven. So the proof should be moved over here. We can indeed find a problem that plays the role of SAT. It's just not such a natural problem. It's the problem PW-SAT2CNF. We're given a Boolean formula that's in 2 conjunctive normal form and a parameter k, and we are asking for an assignment of that weight. One might add that the 2CNF SAT problem, if you drop this weight thing, this is in P. It's a simple problem. Yeah, there's several. It's not only in P, it's also easily solved in practice by very reasonable and fast algorithms. But if you add this restriction on the assignment, it's apparently, okay, it's written down here, it's apparently a hard problem. And this is already a bit surprising, right? But still, this seems to be the most natural problem that you find for the class W1. The proof of this theorem I will completely skip, and the next as well. The point is, what was used in these proofs? So they involve a lot of logic that would also lead too far. So I'll just leave that as a black box. Some clever people have shown that these are complete, so I should mention what this is. If we add the minus here, then this means that all literals appear with a negation in front of them. So an example of such a formula would be not x1 or not x2 and not x2, or not x3, and so on. It's actually a pretty simple form, and even this restriction here is again unintuitive, that this shouldn't be easier to solve, but it's not easy to solve. As I said, we'll skip any proofs why these are W1 complete. But with this as a starting problem, so in a sense, you should remember this one, because that will play the role of a mother of all W1 complete problems. And one connection that's So one connection that's maybe not obvious if you first look at the formula, but which is very simple, is, should have included this as a proper theorem, that the problem P independent set is also W1 complete. Okay, at this point I might add that W1 hardness, not necessarily completeness, but W1 hardness is the goal that we are usually after. So, okay, maybe, okay, I'll move it to the next page. We've already said that W1 is a superset of FPT. That's trivial by definition. And it's a strict superset that is widely believed. You can show if P equals NP, then these two are also equal. Unfortunately, if these two are equal, that does not directly imply that P is NP. But it would mean that the exponential time hypothesis is false. And the exponential time hypothesis says for the 3-set problem, there's no algorithm with less than a constant to the n solution. So there's no 2 to the small o of k algorithm for 3-set. And well, 3-set is a well understood problem. People have found a lot of improvements, especially in terms of FPT algorithms that improve the brute force method, but no one has made progress on showing that it's less than exponential. So for example, there's no quasi-polynomial method. I mentioned this last time, no method with n to the log n runtime or something like this. So this is something that you can rely on for the time being. So that means if a problem is W1 hard, you will probably not find a fixed parameter tractable algorithm. And therefore, we will, for a few problems, show that they are W1 hard. In a few lucky cases, we can also show that the problems are themselves in W1. Yeah, which we'll now do for the easiest ones. And then I'll come back to this. So why is it in W1? Well, we have defined W1 that there is such a nondeterministic RAM. And for the independent set problem, it's actually easy to see why this is accepted by such an NRAM. So we know it can compute a lot of stuff, but then in the end, the non-deterministic part must be only depending on k, on the parameter. So for p-independent set, recall that, so, okay, let's do it a bit slower. Given a graph and a number, the independent set problem asks for a subset of the nodes of size k, so that all these nodes don't have any edges in between them. We've had that a few times. Now, how would an NRAM solve this problem? You would guess k numbers which we can equate with the nodes. We can assume that they're encoded by the numbers 0 up to 1 up to n, if you like. So you guess k such numbers. That only takes, in terms of k, different non-deterministic steps. And then for each k subset, so after k guesses, check the k-squared pairs that they really don't have an edge. Now here, independent set is simpler than other problems that we've talked about. For example, the very trivial brute force method for vertex cover had to check, so that the check of a candidate was linear in the graph size because you had to check all edges, whether they are covered. Maybe you can think about that again and improve it, but if you don't think about it, then it's linear in the graph, whereas here it's really only depending on the size of the solution, which was our parameter. So the number of non-deterministic steps that we need here is only a function of the parameter. That's why it's in W1.
Don't we have to check the complete graph for this edge? I mean, don't we have to go through all edges and check if there is no such edge, meaning it's still linear in the graph size?
Okay, that's a representation issue, you're right.
I mean, are we allowed to, like, give an NRAM, I don't know, access memory that is like, that encodes a graph or something, so you can have like a constant time in checking the edge?
I mean, you can certainly do that if the graph is given as an adjacency matrix. That's what I had in mind. And then, so a RAM certainly can use indexed addressing. That's how it's built. So it can access the matrix entries in constant time.
So you could probably, in linear time before you do the k guesses, you could probably
Right.
transfer it into like...
Yeah, in terms of, yeah, here you can transfer the graph and just compute the adjacency matrix. In general, so I was thinking about the following problem. In general, it might make a difference whether you force your graph to be given as adjacency matrix in the first place or not. But here we are only making a reduction. And this is an FPT reduction. It's not a reduction, I'm sorry, I was confused. No, it's not a reduction, but the NRAM has polynomial time before it has to go through the non-deterministic steps. So yeah, you're right. What we do is, whatever the graph is given like, we first spend some deterministic time, ample time, quadratic in the graph, to compute the adjacency matrix, and then afterwards this can be done with constant time per edge. Okay, so in this case it was also easy to show that the problem is in W1, whereas in other cases we will not be able to show that. But the interesting part is hardness. But in this specific case it's actually very easy because we can use the weighted set to C and F anti-monotone. So people, if you have only negated literals, people call such formulas anti-monotone because essentially such a formula, whenever you make one more variable from 0 to 1, this one goes down in a sense, so less of these literals are satisfied. It's just a name. So we show that we can reduce our mother of all problems to p-independent set. That's probably not a big surprise. So what we have to do is encode such a formula as an instance of independent set. If you look at it, there's nothing to be done. I should write down the general form. So a formula of this kind always looks like this. There's a big AND over all the clauses. And so you have, okay, let's say it's ordered pairs. Doesn't really matter. And then each clause looks like this. Not xi and not xj, or not xj, sorry. There's some given set I that contains all the variable indices that have such a clause or not. It might not be the way that the formula is directly given to you, but in any case, you have variables from x1 up to xn, say, and then duplicate clauses can just be deleted. So you have at most so many clauses, or maybe you add, well, let's be generous, say you don't even care for duplicates. So you don't care for if it's so xi, xj, and xj and xi is two different ones. You will never have more than quadratic number of such clauses, so you can always compute such a set when you're given a formula. And then this is just used as the edge set in your graph. And well, formally we want an undirected graph, so ij, so that there's an ij in I. So you take this as a graph, and you use the same k. So an input to this weighted SAT problem is also the formula and the k that you're asking for. And then you keep the k and take this as a graph. Then an independent set is exactly an assignment so that for any of these clauses, if there is an edge between two nodes, you can take at most one of these. Right? So this is a one-to-one correspondence between formulas in this anti-monotone 2C and F form and this problem independent set. And the parameter doesn't even have to change. Yes?
So the weighted in this p-weighted set still means the number of ones, even though we've negated all the...
Yes. So still the x's have to be 1. Of course, the interpretation, I should have mentioned, sorry. The interpretation in the formula here, so the solution says, okay, we're talking about decision problems. We could easily make this reduction preserve the certificates. Namely, the independent sets in this graph are exactly the ones that you have to set to 1. Yeah, and then here's the clause for every edge, and the clause is fulfilled if you don't have both endpoints. That's the point. Yeah. Okay. It's one-to-one. It's a bit confusing. It's a one-to-one correspondence. So, and this is much more in the realm of the usual reductions that we are comfortable with, right? This is, I mean, this was a very simple one, but I'll show you another one in a second. That's a slight bit more involved, but these are similar to the usual P and P reductions. You only have to take care of the parameter. And what changes is that we have a different mother problem, but now we have at least one problem that we are more comfortable with, namely the independent set problem. So an easy second theorem is that also the p-Clique problem is W1 complete. in essence, you can literally copy what we have here. The difference is that here you should replace no by has an edge. And here you should replace, we add an edge to the graph whenever there's no such clause. And then you're done. This is just because independent set and clique are essentially the same problem, just on the inverse graph. Okay, that was very simple. Let's look at one example that's a bit more interesting. One more page. And that's a problem we haven't encountered. And well, maybe if you see it, you might think about it. It's the problem parameterized partial vertex cover. So the problem is given a graph and a number t and a number k. Then the parameter, big surprise, is the k, and the question is there a subset of the vertices no more than k? Let's say exactly k. So that C covers at least T edges. So this is a generalization of vertex cover, because if you set the T to the number of all edges, you get ordinary vertex cover. But now we allow more flexibility. We can ask for only a partial cover of the graph. And this slight generalization makes this problem p-Partial-Vertex-Cover already hard. So this is a bit more complicated than the reductions before, but still doable. So I wanted to show you one at least non-trivial reduction. So we are only showing hardness. Okay, I don't recall whether it's actually also in W1. Maybe not. So it's natural that we use one of the graph problems we've just considered and show that we can reduce it to a partial vertex cover. So the reduction takes the input of independent set, which is a graph, and the number of vertices we want to have in the independent set. And now we construct a new graph that has a few more vertices and edges. We take all the old vertices, but then for each, Okay, I should write it like this. So for each of the old vertices, we added a whole set of new vertices, which we should just invent a name. Say it's, okay, V for vertex, V for the old one, that's not so great. W, V, I, and we just need a few copies. I from 1 up to, now comes the interesting part, minus degree of V. So what we do is, if a node has not all edges, we fill up with new nodes. And the new nodes are connected only to this old node. So we also take all old edges. But then for all the nodes, we add the edge from V to WVI. Again, for all I like above. Only one. Okay. Maybe I can squeeze it in. Now the interesting choice is that of the parameter t, which is if you come up with the reduction, you would usually just go on now and see at the end what the right parameter is. But we have to set it to k times v. Now in the new graph, every node has degree v by construction. Right, a node had some degree before, and now we filled up that degree up to v by adding new nodes that only this node is adjacent to. Yeah.
But the old nodes has degree v.
Oh yeah, sorry. Yeah, the new nodes have degree 1. Yeah. So maybe a very quick example, but it gets, I guess it gets messy a bit soon. Oh, it's 1, 2. Maybe we should have v minus 1 here, right? We're adding already a node, even if we have all possible edges. But the graph looks like this. So the black one is the original one, and including the blue parts is the new one. That's clear, I guess. So we have to show that an independent set in the old graph is a partial vertex cover in the new graph, and vice versa. So if we have an independent set in the old graph, what's the maximal one? Probably these two, right? Then this covers the maximal number of edges at these two. Is exactly the same, the size. So here k is 2, right? Say it's a yes instance. Then we cover k times 4 edges. Now if we are given a partial vertex cover in the new graph, there's no guarantee that we only pick black nodes. It might happen that we have some blue nodes as well. But if we ever pick a blue node, we can either remove it from the partial vertex cover if the black node is also in, or if the black node is not in, then we're better off by picking that node instead of the other one. So we can assume without loss of generality that there's also a cover that picks only nodes in the old graph. So why is that an independent set in the original one? because whenever we have, so assume we picked these two as a partial vertex cover, then they have an edge in common. So they together cannot have the full number of edges. Is that clear? So I should probably write down these arguments in detail, but maybe the example is sufficient to convince you. That's an example of a non-trivial but still not so hard reduction. And here you see that also it's involved a few changes of the parameters. But the important parameter, so this was just part of the input. The parameter in the FPT sense remained the same. That's the same K. And that's important for the FPT reduction. Okay. Maybe this is a good point to stop, even though we started a bit late. But I think it's better to cover this in a bit more detail. And then we'll start next time with the algorithmic part of the FPT theory. So this is as far as I want to go with the complexity part. You are now equipped with machinery to show that a problem is W1 hard. I mean, in general, so in principle, you can show, building on the problems that we've shown, that there are W1 hard. You can take these, reduce them to a new problem, and show that this is also hard. And if you're not succeeding, then maybe the problem is not hard, and you find a good algorithm. I think there's one last point that I should make this time. We've now talked about the problem partial vertex cover. What about vertex cover itself? Is it easy or hard? So we needed a generalization to show that it's hard. That might, from a didactic point of view, already tell you that it's probably in FPT. Up to now, we've only seen this very stupid brute force method, which had a non-FPT runtime. But in fact, this is true. Vertex cover is one of the easy parameterized problems. And the idea is just to replace the very stupid brute force method by an only slightly stupid brute force method, which works as follows. That's a nice introduction to the algorithmic part next time. So you pick k edges from the graph. If the graph doesn't even have k edges, it's a very simple instance. You can just pick you can pick from all the k edges one of the endpoints. That's still less than k, so you have a vertex cover. So if you have more than k edges, you pick any k. And then for each of the k edges, you have two choices. Any of the two nodes must be in the vertex cover. Okay? You don't consider all edges here, which means that it might happen that you'll never find a solution to the problem here. But if you don't find such a solution, then there is none with k, because all vertex covers have to also cover these k edges. So you pick k edges, and for each, I'm very unspecific here about how this works algorithmically, because we will talk about that in depth in the next 2 lectures, I guess. So, and for each edge, recursively test both endpoints. So as I said, deliberately unspecific. But it's clear that there are only 2 to the k different combinations. And that gives you just 2 to the k different candidates for a solution. And you can check whether whether any of these is a vertex cover.
But the solution that you get isn't necessarily a finished solution for vertex cover yet.
That's true. But if none of these works, then there is no vertex cover of size k. So it's the decision problem, right? Is there a vertex cover with k nodes? And if the answer is no, then the answer is no, nothing to do about it. But you will never overlook a vertex cover if there is one, because if there is a vertex cover, it has to cover the k edges that you picked. And that means for any of these edges, any one of the 2 endpoints must be in the cover. And then that means you tested that combination. Yep.
But if you
Still not convinced.
Well, if you get if you don't find a vertex cover, basically,
By this?
you're able to. Oh wait. Oh, okay, now I understand it.
Then it helped you. Okay, as I said, very unspecific, but yeah, we'll see how we can formalize this. So that's why I didn't show that vertex cover is W1 hard, because it isn't.